Nicely. So you see, you can go for different seed values. So which seed value will give a good result? That is to be determined. So two ways of doing this. First thing is that this is one problem. Maybe genetic algorithm, maybe PSO or bacteria foraging, whatever, you can use the algorithm to optimize this. And second option is that you set one parameter and you generate the random number. Okay? When the random number is generated, you go for various tests. Three tests are prescribed normally, statistical test. One is called the monobit test. This earlier slide is not coming. Yeah, that's why this is scattered. So one is called the monobit test. Second one is called the serial test. Third one is called the Poker test. Three tests. I think it is available in the net. Anywhere you can download it. If your system of this parameter passed by these three tests, I can say that whatever the random number I have generated, not only for this neural computing or cryptography, in any cases, if you need some random number and if you want to test the random number, that whether that random number is truly random or not, you go for these three tests. And if these three tests satisfied, statistically you can say that your random number is true random. So first test is called the monobit test. There is a formula for the monobit test. I think it is not coming. The previous slide it was there. You can get it from the net. In monobit test, it used to test bitwise, either 0 or 1. So that means the count will be number of zeros 1, number of zeros and number of 1. Suppose I have 10 bits. So 5 zeros and 5 1. So it's fine. Is it sufficient? There may be 5 0 followed by 5 1. Then it is absolutely biased. So that's why only monobit test is not satisfied. And then after that, it used to go to the chi-square. We have a chi-square value of the 0.05, that is 5% uncertainty. So chi-square test you have to go for it. So chi-square test, you know that the Pearsonian chi-square you normally use. Formula is available on the net. Nowadays no problem. You can download it and go for it. So you see that if it is, this is a critical value of the parameter. So if it is below that, it is homogeneous. Normally, chi-square test gives the homogeneity. But in cryptography, chi-square test we normally go for the heterogeneity. That means it should be more than that. But here it should be similar. So that's why it should be less than that. So if it is 3.84, less than 3.84, that means it is good. That means that satisfied, but bias is there. So second test is again formula aspect. You see? Yeah. You see that the previous two slide was your serial test and poker test. So it's not coming. I don't know why it is not coming. So serial test is used to take 2 bit at a time. That means pair of bit. There is a formula. Again, it will come on that, and chi-square value will be computed. So monobit test satisfied. your uh, serial test satisfied, then you go to the Poker test. What is the Poker test? There is a formula, so it's not showing. The formula is that you take starting from 3 bit at a time, 4 bit at a time. So if your string is 16 bit up to 8 bit, 50% of the length of the string, and for each case it should satisfy separately, then you can say that whatever random number you have generated for whatever be the purpose, it is exclusive of this, not for the neural computing. It is for any cases, anywhere if you use the random number, that random number will be truly random. So you go for these 3 tests and you just get that these are the random numbers. So some of the KFT maps are showing here. So just I am skipping this. And then you see these are the functions. Binary bit generator. How? So I can take the median, less than median, 0, more than median, 1. Because all the chaotic equation gives a real value. So from there, binary mapping should be there. So I'm just keeping this. And this is, you see, the sensitivity of the chaotic equation. You see, we have a value of 0.30 and 0.301. You see, this is ups and down. So that is the sensitivity of the chaotic equation. And you have to choose a proper system parameter. So how do you choose the system parameter? That you can go. So unload calculator, I think all of you know. I'm just skipping that. There is a mathematical. You see, your matrix-based equation. Again, it is a cyclic equation. After sometimes it generates the original one. You see, I'm just showing you very. Yeah. You see, I started with this 16, 10, and I'm going for this is a computation, simple computation. You see, I'm generating. So any one in the middle, I can go for the equation. Then, if you go for the rest computation, you can generate the original value. It is called the decoder. So anything you can go for it. Yeah, here it is giving. You see that iteration 1, iteration 2, iteration 3, iteration 191. So somewhere you see here you can give it. That good scrambling of the image, and then you go for here you get you see original. So if we use this chaos base encrypting, so we will get like this. Yeah, it is. This map is called also the logistic map. So you can search in terms of the logistic map. It is a chaotic map. Again, it is learning techniques. So here I am just keeping these things. These are not my intention for today. So this testing is there already. Gone for it. Yeah. Now let us tune some network and see the result. That means my intention is that I shall tune the network. I shall generate the key from the both end of the network, and I shall use some lightweight encryption technique. I shall encrypt it and I shall go for some testing. And various test results I shall see. So implementation algorithm I am not going, I am going only for the result. So we have tuned the SOM network. So SOM network is a very sensitive network. However, we have tuned it. So on tuning the network, you see, these are some of the parameters. So I can go for 2D and 3D. I am not going inside into that. So this is the protocol when I am tuning, because we have used the two computer systems and we have even written the protocol also for exchanging one value. When it is computed from my network, it is exchanging a single binary bit. There also when computed, they used to exchange one bit. Is this bit is 1 or 0, then the values corresponding that particular intermediate nodes are updated. How it is updated? Using some rules. So we have used Hebbian, anti-Hebbian and random walk. Then after certain period or iteration, both of the network will be identical. This is called the tuning. So that methodology we have used, and using this protocol, we have tune the network. And then we have gone for the fractal triangle based encryption. I am not going into that, I am going to result. These are all these things explicitly given. Yeah. Let's see, first one is the your frequency distribution. That means what was the frequency distribution in the input file and what was the frequency distribution after implementing the method into that particular data. You see, frequencies are distributed. Then we have one the floating frequency. What is the floating frequency? It's the local information content in the individual point of the document. You see the result. Here you see this is the floating frequency for the input file or input text or input data. But you see it is distributed over the complete region. It is a sum network. Then autocorrelation you have computed. You see this is the autocorrelation of the input source. Now how it is decorrelated, you can see that. This is a sum network. You see this is the chi-square values. You see that chi-square values we have compared with the triple days and AES. So we know here the two famous method, AES and triple days. So here you see some networks are almost at par with that in terms of the chi-square values also. And again, you see we are testing here the heterogeneity of the text, because how much scrambling of the text I am going, that means that much good encryption is going for that. So here it's a good, that means I am not using any TDS or AES, but I am just tuning the network and I am generating the keys and I am encrypting using very simple lightweight encryption technique. And you see various different types of files you have used: executable files, text file, doc file, and results of the tuning. Here you see we have used 3 key length. One is 128-bit key length, another one is 192-bit key length, and third one is 256-bit key length. You see what are the cycle of tuning? You see it is 2500, it is 3200, and it is 2200. Please keep in your mind. I have used single hidden layer. I have used some input vector. I did not use chaos theory. So it is a simple neural networks. And what is the tuning methodology? It is KSOFM, sum network, not tree parity machine. We shall compare later on with the tree parity machine. So this is the cycle with single hidden layer. That means 2500 and 4200 for the 256-bit key generation. So now the overhead of parameter passing in the protocol is much in the sum network, and is very difficult to tune, because we have started with the sum network. We have faced a lot of problem. I think around 2010 we have a lot of papers on this sum network. So around 2010, I think 11 we have done all these works, and it has published 2014. I think 116 one paper published. 5-6 years we are taking. It's a long good journal. Is that at that time it was very difficult to publish this paper, but concept was not there. So then let us consider that 2 hidden layers. I am increasing the synaptic length of the network. So I am now using 2 hidden layers. So double hidden layer perceptron DL DHLPT. Okay. Now I am going for the synchronization. Yeah. So I have 2 hidden layers. We have number of input neurons. We have hidden, and yeah, the method is here. So we are using again the same, only signum functions we have used. What is used in the neural network? So signum function is SGNX equal to -1, x less than 0, equal to 0 if x equal to 0, 1 if x greater than 0. So it's very simple signum functions we have used. Now again it's a problem. This protocol. So we have used the simulated annealing based encryption here. So let's, yeah, here some fitness function we have used, and some crossover probability mutation also we have used, and encryption we have gone for. And here for extension of the key, normally in the cryptographic system you see you have used a triangle. So if you unfold the triangle, so length of the key will be enormous, 3 times. So you have used that technique to extend the length. So let's see the output. Yeah, you see this is your frequency distribution. Again, this is your floating frequency. You see how the floating frequencies are decorrelated from here. This is a bias. You see mostly here the values are here and the values are here. But in the entire region the values are completely different. So I have increased the hidden layer from 1 to 2 1. You see. Now very interesting things are there. Now here autocorrelation. You see how completely decorrelated. Here you see it started here only. And you see here it come here only. But you see from complete range it is a very good result it has given. And then again chi-square value. You see AS, PDS, sum and you see almost same. But why we should go for more hidden layer? Definitely decorrelation is more. Yeah, all types of files are here. And now you see we have tuned multiple types of network, not a single type of network. Multiple network we have, you see, size 8, 16, 24, 24, 32, and then various layers. You see, and then we have one for Hebbian, Anti-Hebbian, and random walks for the synchronization. You see, the synchronization for the Hebbian is this less, and for the random walks is more. It is for what? It is for 120. Now, very interesting result you will see that if you change it to the 192 bit, it is less time is for the anti-Hebbian. There you see, anti-Hebbian is giving the less. Again, you extend the bit length to 256, random walk gives a good result. In all cases, whatever we have studied and implemented, you see random walk for the high key length is good. And Hebbian for the low key length is good. And most interestingly, you see I have increased the layer. It was a first single hidden layer. Now I have used two hidden layer. Now evening time, it was here. More than 3,000. 3,000 around. Now 2,000. That means I am increasing the heading layer. So what I was talking at the beginning, that I am using 16 layer for the max pooling, for the you see various calculations. That means enormous time will be needed. Absolutely no. If we increase the synaptic length, that means the tuning time is drastically reducing. You see here, you see here, you see 3,000. It was 4,200. So it is drastically reducing. But I have increased the synaptic length. So there are some problems. I'm not going into that. You see, identical random seed was the major problem. That means the seed given here and seed given here are different. So that's why the tunings are not coherent. So for that reason, we have gone for chaos-based tuning. I have double hidden layer, but I have incorporated the chaos to generate the random seed at the both end, or random input vector at the both end. Now what is the effect? The effect is that this is a nonlinear dynamics. So I am incorporating a nonlinear dynamics into the system with two hidden layers. So what is the effect? Let's see the effect. So again the protocol systems are there. I am just skipping this protocol systems. You see only the chaos, two hidden layer is there. And here we have gone for the GMS infusion technique. You see inform crosswalk, mutation, crossover and mutation probability you have taken. These are some examples of the infusion. We have gone for the example here. Yeah. You see again the same thing for the frequency distribution, and you see that this is your floating frequency, but see the floating frequency. It's improved a lot, and autocorrelation also you see improved a lot, and it's a complete range is identical. But here you see we have curve of this time. And also chi-square values, you see AES, PDS, SOM, DH, LP, and this is chaos. You see, when we are using the chaos, almost identical results we are also getting for all types of files. And again the same thing, if you go for the 128-bit key, then definitely here you see Hebbian rule, then 192-bit you have the anti-Hebbian, and if you 256-bit it is random walk. So for the tuning, random walks for the high key length or larger key length is always good. And now tuning, you see I have used chaos. It is a nonlinear dynamics. Now what is the tuning time? From 3002? Drastically reduced again. That means I am increasing the complexity in terms of the mathematical computations. But neural computing is such a system where I am getting the efficiency. That's why this is 16 layer, 15 layer, 14 layers. We are not thinking about that. We are only thinking about the output. The reason is that this is the mathematical things, but we are doing it. We have done it most earlier than whatever this nowadays everyone is doing that. And now you see this is awarded I think 2018. I think. So now I am increasing another heading layer, triple heading layer. Let's see the effect. Yeah, this is the network. So we have three heading layers, and number of neurons are more, but one output layers. So we are tuning in terms of the learning rules. Same learning rules we are using, and we are using some protocol systems. And here we have used AND colony for the encryption. You see different encryption we have used for each case. These are some of the examples of the encryption. I am skipping that. Yeah, these are the results. You see, again the same plotting frequency, almost. You see, this is the input file, and this is the output stream. This is your autocorrelation. This is your chi-square values. Everything you have computed, but you see the values are at. And again, you see the 120-bit. It is your Hebbian, then your anti-Hebbian, and then random walk. And you see the tuning time. It is from 3000 coming down here 2000. But I have increased one hidden layer. I have assisted with the chaos theory. I have inserted the nonlinear dynamics. So you see from 4000 is coming out the around 3500. So now another thing is that I am talking about the cryptography. I am talking about the security. So what is the point of tuning the complete network? This was one of our questions at that time. That should we completely tune the network? But in most of the cases we are tuning the complete network. In any neural computation here, we are using the complete network. Now let's see the effect that if we go for a group tuning. We have tried the group tuning and we have successful. That means you see you are the intruder. So I am tuning the complete network. And I am tuning a particular portion of the network. You don't know what portion I am tuning. I have a huge architecture, but a part I am tuning. So now my next chapter is that tuning of the grouped triple heading layer. We have used the triple heading layer, but we did not tune the complete group. We have tuned a particular portion of the network at both ends. That means only some left child we are tuning. So only communication that left child. You don't know the network. But identical networks, so you tune the network. But definitely the tuning time is more. because I have to search a particular group and I have to tune only that particular group in spite of a complete network. So that takes more time, but it is most efficient because most security implied things, because the intruder does not know which group of the network has been tuned and what was the weight vector for each group and what was the weight vector for the edge and other nodes, intermediate nodes. You see, and we have tuned it, and we have particle swarm intelligence we have used. So I am not going into that, all the computations and all that. You see that the frequency distribution is enormous improved, and plotting frequency also improved a lot. And then autocorrelation is a good autocorrelation also we are getting. Then for all the cases, you see AS is to 26,000, but here you see here we have some, yeah, this one 36,000. So that means I am enhancing the security. I am again enhancing the security of the, you see, for the various types of files. I am enhancing the security for all cases. Yeah. But definitely the same things are there. I'm just going to that particular, yeah, this line. You see, it is 7,000. This overhead is more. Definitely it has to be more because it's searching the group among the network, complete network. Complete tree you have to traverse. So you are using a tree traversal algorithm when you are tuning. So that algorithm takes more time because I am not sequentially going for the DFS or BFS, whatever may be. But you see, sequentially we are doing that. But here I cannot go for the sequentially. I am doing the random one. That means I have to find out the particular group and then I have to tune that particular group. That's why you see, which is, that means the tuning time is more, but it is most secure. So these are some of the things. I think this is from the Starlink's book. It is written there based on the security of the keys. So we are going for 256 bit chip for better security. Yeah. Now the NIST test bed. What I was talking about, that they have a white paper for the NIST test bed. So in NIST website you can download that NIST test bed. So all things are there. So we have 15 tests prescribed by the NIST. So when you are writing an algorithm for the encryption or when you are writing the algorithm for the authentication, so how many tests out of these 15 tests it is passed, so that you can see, and as a result you are going to benchmark your algorithm with the test bed of prescription from the NIST. It is not your test, and the test to be satisfied using some parameter. That parameter has been specified by the NIST. So first is the frequency test, which is for the monobit. Already we have discussed. So for the monobit test, you see we have 1, 2, 3, 4, 5, 6 network. So we have started with the 3 parity machine. So we have on the SOM network, double hidden layer, chaos, double hidden layer, chaos, triple hidden layer, chaos group tuning. So for frequency test or monobit test, you see this is the expected proportion. So if your observed proportion is more than expected proportion, then your test is passed, otherwise your test is failed. So it is defined by the NIST. It is not our algorithm. This is the test bed condition of the NIST. So you see, in all cases for the monobit test, it is passed. So I have told you what is the problem in the monobit test. That means out of 10 binary number, 50 and 51, that is also random number. So that has a problem. For that, all methodology has passed here. Now let us test for the frequency within a block. how many string of maximum length within a block will be there. So for that test, you see your three priority machine unsuccessful and all others are successful. That means you see when I have written this 5 algorithm, so 5 algorithms are good in terms of this frequency within it. That means my 5 algorithm is passed for the first test as well as for the second test out of 15. Let's go for the run test. So this is another test prescribed by the NIST. So what is the run test? The total number of zeros and ones runs in the entire sequence where a run is an uninterrupted sequence in the identical bits. So now let's see what is the expected 972766. So here you see all are successful. Along with the T parity machine, this is one existing. So this one our algorithm. Now test for longest run of ones in a block. This is another test. So methodology is given. You see here SOM network fails. That means out of 4 tests, 1 test is failed by my SOM network. You see, when you are writing the paper on this NIST test bed conditions, that is your benchmarking. That means these algorithms are good more than this, better than this. That means you can quantify that in terms of that. Then random binary matrix rank test, another test prescribed by the NIST, and this is the condition that here T parity machine is unsuccessful, but other 5 networks are successful in my test bed condition. Then go for the discrete Fourier transform, which is called the spectral test. Here also you see tree parity machine and SOM network is unsuccessful. So at the beginning I was talking about the SOM. This is a very difficult, very sensitive network, SOM network. It's very difficult to use for the neural computing. Then non-overlapping template matching. So it is another test. That means it is purpose of the test is to reject the sequence that exhibit too many occurrences of a given non-periodic pattern. Here all are successful because all values are more than the expected proportion. All of the values are more than the expected proportion. So overlapping template matching test. Another test is there. So here you see your tree parity machine is unsuccessful and other networks are successful. Then Myers universal statistical test. This is another test. What is the purpose of the test? Is to detect whether or not the sequence can significantly compress without loss of information. It's called the Muir test. So they are all are successful. Again, linear complexity test is another test. So whether a sequence is complex enough or not, normally it tests. So here also all the tests are successful. Then serial test. So already I have discussed the serial test. It used to take the 2 bit at a time and go for the timescale values. Here also your SOM network and tree parity machines are unsuccessful. Then approximate entropy test. That means you are obtaining the entropy and you are testing that entropy. In that case also all 6 proposed algorithms are successful. Then cumulative sum test. Here also your tree parity machine and SOM network is unsuccessful. Then random excursion test. Here also you see your tree parity machine and SOM network unsuccessful. You see that means you cannot take the SOM network for security purpose. That benchmark is proposing to you. That means in terms of benchmark you can reject one algorithm. You see, random access and variant test. Here also some network is unsuccessful. Now you see that out of 15 tests, most of the cases some network fail, but other networks are good. So in this way, you can benchmark your algorithm in terms of NIST test bed. Lot of other test bed conditions are there for various computations. You can go to the NIST site and you just find out what are the required for you. I don't know. We have found out that for our computations in terms of the wireless security, just we have used that. So I can use various domain. So I am giving you one steganographic application. So very interesting application, legal document application. You see steganographic application in terms of legal document. Suppose there is a dalil. What earlier written on the dalil? So handwritten. A lot of signatures are stamped. We cannot understand that what is written there. But nowadays, what is that? This is written on the MS Word. Most of the cases there is an editor. So you are editing the text. So suppose I am writing some text here. You see, and you see this is being transmitted, and someone is getting that, and he has changed it. How he has changed? You see the change. You see that maximum has been changed to minimum. Okay. Now you see that your 3-4 place, I think is this place. Strong has been changed to weak, and I think 3 places it has been. Yeah, another is changed. So now these are the changes. Change होएगा चेक एखाने आ सकता है. ना positive and negative होता है. So 3 change. So now how do you authenticate that? That this has been changed. At a legal document, আমি আমার নামটা লিখে নিয়ে চলে গেছি MS Word. So this is lot of works are going on in the court for this document verifications and all other things. Now here we have a methodology. This paper published in the ACI journal. And this is research work of another scholar. So I have the original document and we have the changed document. So I need a technique to authenticate. So suppose I am generating MD5. Very simple case. I am generating one hash function. So I can use MD5 algorithm. I can use SHA1. I can use my own algorithm. So it is one-way hash function. It is one-way hash function, and I am generating the MD5. Then this MD5 is embedded. That code is embedded on this as a steganographic approach. So I didn't cover that as steganographic. So you can just study. I have that book. You can read that. So it is called the invisible communication. That means when you embed, the visual quality of this image will not be changed. If you compute the PSNR of this value of this image, it will be more than 30-35. This is called the steganography. Then you communicate, and also you communicate this code through a private channel. At the receiving end, I have got this. So how do you authenticate that? First, once again I shall compute for the one-way hash function. That means I shall generate the MD5. So let's you generate the MD5. And then you extract the MD5. And you take the data from the private channel or the confidential channel. So you just compare. If all 3 are matches, then you can say that this legal document is authenticated. So definitely we have to have a third party who will keep your data. Who will be the third party? Maybe the court, database of the court, or maybe some gateway, just like your transaction. All the monetary transactions, we have the gateway. If your transaction failed, it used to refund your money. That means we have the RBI guidelines. So that type of guidelines you can go for it, and you can authenticate the legal document. So the thing, whatever I have deviated from the normal sequence of the cryptographic system is that we are going for tuning the network, and we are generating the key at both end of the network without transmitting the key or exchanging the key. And definitely we can go for a variable size of the key and algorithmic complexity. When we are increasing the synaptic length, synaptic depth, input vectors, even tuning cycle is reducing. So these are some of the, so these are in very short. I have one very short, I don't know how much I can give you the justice. So this is my lecture in terms of this neural computing and neural cryptography.
Sir, the addition of the hidden layer increase non-linearity definitely, and it also helps us to find pattern within that.
Yeah.
And which is inherently help us to increase the predictability.
Yeah.
Here you are using the hidden layer to increase the to improve the non-linearity to increase the
Randomness.
So in isn't it risky to add increasing a hidden layer in a system? Isn't increasing the inclusion of the hidden layer reduce the randomness?
No, it is increasing. You see, when I am going for tuning a path, instead of tuning a complete network, so randomness is increasing. Because you see, the more computation is needed. Ultimately, one layer. So I have lot of edges, lot of intermediate nodes, again edges, intermediate nodes, again edges, intermediate nodes. So you have multiple type of computations, multi-layer computations. So computational complexity also increasing, and chance of guess is reduced.
So one thing that apart from the serial test and poker test and monolith test, there are also certain tests also used that is entropy.
Yeah, lot of other entropy test is also there.
So is it sufficient if we find that all three tests?
No, entropy test is not for the randomness. Entropy test is to ensure that quality of your input information is at par with the input. The purpose is quite different. But here we are ensuring the randomness of the input vectors. True randomness of the input vector is quite different perspective.
Sir,
Yeah.
in case of WSN, security and privacy is concerned, but in our life, energy efficiency is also is a concern.
Yeah.
But when we are doing a procedure which needs more time, that means it requires more energy consumption.
Definitely.
But
But
the node has not
that much of energy. That's why you